All right, so here's a model of a solid. Okay, so here's a solid object. And here's a model. The atoms are fixed locations. Okay. There's interatomic forces or intermolecular forces that are modeled by the spring. Okay. And at any given temperature, these guys are vibrating about their equilibrium position, and you learned that the temperature is a measure of the average kinetic energy. Okay. Now, let's say I heat this solid. What happens when you heat a solid? These molecules vibrate with a greater amplitude, so their average kinetic energy increases. Okay. And it expands, meaning so when you're adding energy, its kinetic energy increases and its potential energy increases as well. Okay, so when you're holding a spring, when you stretch a spring, its potential energy increases. Okay. So in fact, when you add energy, equal amounts of energy goes to kinetic and potential energy. To every degree of freedom, you contribute equal amount. Okay. So since the potential energy increases, these expand. Okay, so the interatomic distance increases. Okay, and so since every molecule is further away, the total length of the object increases. Okay, so as engineers, we want to know how much the length will increase. So this tells you the increase in length is equal to the original length times the increased rise in temperature times a number that's dependent on the material. Alpha is the linear thermal expansion coefficient. Okay. And these numbers are important enough where they give you, material scientists will give you these standard tables. So aluminum, for instance, this number, okay, so here's how you think about these numbers. Okay, so here's the expansion. Alpha, if you raise the temperature by 1 degree Celsius and you take 1 meter, so this is 1, alpha tells you how much of that, how much expansion you'll get. Okay, so this number is telling you alpha is 25 parts in a million. You take a 1 meter aluminum rod, it increases by 25 into 10 to the minus 6 meters. Okay, L was 1, you raise its temperature by 1 degree Celsius, it increases by that amount. 25 into 10 minus 3 millimeters equal to 0.025 millimeter. So you take a 1 meter aluminum rod, you raise its temperature by 1 degree Celsius, its length increases by 2/100ths of a millimeter. Here's a millimeter, right? It's increasing by 2/100ths of a millimeter. Why the heck do you care, Jeff?
It might have things like engines, pistons moving inside the engine, you're going to get friction lock and
Yeah.
C's, you could be all kinds of things.
Yeah. Here's an everyday phenomenon. Okay. Every bridge, you have these thermal expansion gaps. The temperature changes between summer and winter. Okay, so in the winter, the spans are the smallest, and in the summers, the spans expand. And if you don't leave these thermal expansion gaps, here's what would happen to the bridges. The spans would push against each other and they would crumble. Okay. Those cuts on the sidewalks that you see, those are thermal expansion gaps. So if they didn't have those cuts, the sidewalks would crumble. All right, so so you have to account for all of that. Okay, so next time you walk over the bridge, you'll see those thermal expansion gaps. So here's a good homework. In the summer, the gaps are the smallest, of course, and then walk now and then walk in the summers. So here's a bridge in Michigan. It's about a kilometer long. A kilometer is from here to Krispy Kreme donuts. Okay. And the bridge between the winter and the summer, it sees a 100-degree rise in temperature. And its length can increase by 1.5 meters. 1.5 meters is your height. So all those gaps add up to that. So here it is in the winter, here it is in the summer.
Are they able to like calculate that to make sure the
Challenge.
Yeah.
things are the correct
Mm-hmm.
length?
Yeah. Here, somebody didn't calculate it right. Here.
Oh.
Yeah. So, of course, you don't want to, I mean, you want to leave room for error, but you don't want to leave too large a gap either. Yep. Mhm.
Why do they use thermite to put the tracks together? Because as far as I'm aware, there's not thermal gaps, expansion gaps on railroad tracks.
Oh, there are.
You
Every,
want to bet $1?
huh?
You want to bet $1?
I'll bet $10.
I take you up on that.
All right. We can play golf at the Daytona Municipal. Kill two birds with that.
No.
I'll collect. All right, so here's the Trans-Siberian Railway line, 10,000 kilometers. That's from here to San Francisco and back. The thermal gaps are 8 kilometers long. They would add up to 8 kilometers. So this stuff is real. You might see this in buildings as well. On if you go over Seabreeze Bridge and hang the first left, you go east on Seabreeze Bridge, and there are buildings built right close to each other. There's thermal gaps between buildings. So here's an interesting thing. Okay, so here's the question. So here's a washer. The question is, how does this gap expand when you heat the washer? You guys understand the question?
When you said when you heat it,
Let's say I heat the washer. How does this gap expand? Okay, so here's how you think about it. It expands exactly like the material surrounding it. Okay? So if this were aluminum, this gap expands as if it were aluminum. If this were steel, it expands as if it were steel. Okay, so here's how you think about it. Think of a solid disk. When you heat this, this expands, and that would expand just like that, the surrounding material. Okay, so if this material was not there, the gap would expand just like that. So here's an interesting thing that can be done with a ball socket joint. Of course, if you want to make a ball socket joint, when the temperature is cold, the ball doesn't fit the hole. So to make it fit, you just heat this, that expands, and then you fit the ball in there, and now you have a ball socket joint. Okay, this stuff is also used in, similar stuff is used in, you have seen these hunks of metal flying about. Okay. Of course, you want to make them as light as possible, and so the metal you use is aluminum. Okay. So you have these aluminum screws that you're screwing onto plates. Aluminum strips very easily. So how do you get around that?
cool the aluminum.
Yes, so you have these holes, and what you do is you cool the screws. You dip them in liquid nitrogen, and then you screw them up. Okay? And then when they warm up, there's a tight fit. So these kinds of tricks are used all the time. Okay, so the rate of, so here's okay, so the increase in area is 2 alpha. Here's the linear coefficient of expansion, 2 alpha times area times the rise in temperature. Similarly, the volume of your gas tank increases the same way as the surrounding metal, okay? And the volume expansion coefficient, beta, is 3 times the linear expansion coefficient. Okay? That's assuming the material expands the same way in all directions. So here's a very interesting graph. Okay, so let me show you what is interesting about it. The density of a material is mass divided by volume. What happens to the volume of a material as I increase the temperature?
Volume increases?
Volume increases for most stuff, for almost all stuff. And so as temperature increases, since volume increases, what happens to the density? Decreases. All right, so if you increase the temperature of a substance, the density decreases. Look at this guy. This is for water. As you're increasing the temperature, the density is increasing. And that happens in only this small window, 0 to 4 degrees. After 4 degrees, it's behaving normally. You're increasing the temperature and the density is decreasing. So this small window, this behavior is odd.
Is it because of how ice is less dense than water?
This is water. It's got nothing to do with ice. I'll tell you about an interesting consequence of that. We are thankful for this. And again, it's amazing in nature you have all these crucial phenomenon. And it's a small effect as well. See, this is 10 part in 100,000. Okay, that's a very small portion. 15 parts in 100,000. Okay, so here's a very interesting consequence. Do you guys know how to freeze a lake? You never frozen a lake? What have you been doing?
Living in Florida?
And living in Florida, okay. What's that?
Jacksonville last weekend.
Yeah. So here's how you freeze a lake. So let's say you have a lake. You want to freeze a lake. What you do is you go home, flip a switch, and turn the air temperature to minus 20 degrees Celsius. Okay, now your lake that was at 10 degrees Celsius, what happens? Heat starts flowing that. All right, heat starts flowing that way, and let's say eventually we're going to fast forward all of this stuff. We're going to freeze it in 30 seconds. So the lake has become 4 degrees Celsius now. Heat is still flowing because this temperature is still higher. And okay, the entire lake is at 4 degrees. Okay, now this is at 2 degrees Celsius. Okay, at 2 degrees Celsius, this is less dense than the water at 4 degrees Celsius. This water is less dense than this water that was at 4 degrees Celsius. Now that won't sink. Heat still, so this becomes 0 degrees Celsius. Eventually this will freeze. And now the density of ice is less than that of water. And this won't sink. Oops. And now this is a good blanket. Okay. Now heat is not flowing as much. Okay. So you tried to freeze the lake, and all you could do was freeze this portion, and this portion was liquid. And this is important for us because fish can live in 4 degrees Celsius. Okay, so when you try and freeze a lake, only the top portion freezes. Okay, and that's thanks to this graph, this little thing. Okay, so very important for life, this little bump in the graph. All right, so here's a model of a solid. Atoms are in fixed positions, and at any given temperature, they have kinetic energy and potential energy. Okay, if you add heat to the okay, so if you add heat to the substance, so let's say your solid has 8 atoms, you add 160 joules of heat, okay, 20 joules will go to each of the atom, and 10 to kinetic energy and 10 to potential energy. Okay, so equal amount of heat is added to each degree of freedom. Okay. And when you bring this guy in contact with another object that is at colder temperature, this internal energy flows from here to there, from the hotter object to the colder object. The average kinetic energy is decreasing and the average potential energy is decreasing by equal amounts. Okay? So internal energy is the random kinetic and potential energy. Okay? And heat is that energy flowing from a hotter object to a colder object. Okay, so heat is that internal random kinetic and potential energy. Internal energy or thermal energy of the system is the random internal kinetic and potential energies of the microscopic constituents of the system. Okay, there was a time when we didn't know heat was that. It was some form of energy. We thought that it was some kind of fluid. So when heat flowed from a hotter object to a colder object, it was this heat fluid that flowed from an object. And once we realized that heat was a form of energy, and this happened not too long ago, 250 years ago, then we had to find, so heat was defined as a calorie. 1 calorie was equal to the heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. That's how we had defined heat. Okay. Once you realize that it was a form of energy, joule was the unit of energy. Okay, now I'm mixing up the time things, but joule, when you lift this guy up, you calculate how much energy, potential energy it has, mgh in joules. Okay, and then you heat water, you know how many calories of heat you needed. Okay. So what you wanted was the conversion between calories and joules. And Mr. Joule did this experiment to figure out the conversion factor. And here was the idea. Okay, so when this guy falls, it turns the spindle, which warms up the water. You measure how much temperature the temperature of the water rises. Okay. You can calculate how many joules this lost and how many calories that were converted to. Okay. And that's how Mr. Joule found out 1 calorie is 4.186. 1 calorie is 4.184 joules. Okay. And that's why we named the unit of energy after Mr. Joule. Yeah. So Joule was the first to determine the mechanical equivalent of heat. Yeah. So that's what this experiment was about. You guys understanding this, or is this information overload? I'm sorry I had to go this fast, but we have to do it. All right, now we'll talk about something called specific heats. And we talk about specific heats for solids and liquids. For gases, we talk about molar specific heat. The amount of solids and liquids are easily measured in kilograms, in mass. But when it comes to gases, an easier thing to measure is how many moles you have. Okay, so we define specific heat for solids and liquids. Okay. So let's say here is a solid, you add heat to it. Okay, there's the mass, there's the specific heat, there's the rise in temperature. All right, so what we are saying is the following. Oops. Okay, you add the same amount of heat to two different substances, the same mass, what you find is their temperature rise will be different. And that's because their specific heats are different. Okay? What the specific heat tells you is how much heat do you need to warm 1 kg of the substance by 1 degree Celsius. All right, so, and this is the property of the material, specific heat, and it's very important. And so that's why you have specific heat of all these different substances. Okay. Here's the specific heat. So water has a large specific heat. Okay. The specific heat of water is 4,186 joules per kg per Kelvin. A kg of water is about half of this flask. Dirt essentially is silicon dioxide. Earth has a specific heat of 700 joules per kg per degree Kelvin. Look at that. The specific heat of water is 6 times greater. Okay, so let's look at that formula again. Q is mc delta T. Okay, let's say we put the same amount of heat into dirt and water. You take the same amount of dirt and water. The specific heat of water is 6 times greater, so the temperature rise will be 6 times less. You don't change the temperature of a body of water easily. Okay. All right, so let's see what happens. Okay. Let's say during the day, you're shining the same amount of radiation on both land and water. You just saw that the temperature of land will increase 6 times greater than water. Okay. This air gets warmed up to a higher temperature, it expands, it gets less dense, and it rises up. It leaves a low pressure. Here's a high pressure, and you have air flowing from here to there during the day. Okay. At night, the heat content of land is smaller. It cools down faster. The heat content of water is higher. It's still warm. And so now this air is expanded, rises up, leaves a low pressure. And so you have a high pressure here, and you have air blowing from here to there. So during the day, you have a breeze coming in from the ocean, and at night, you have a breeze blowing into the ocean. So if you build a house here, not only do you have a good view, you have a constant breeze. And also the temperature is fairly steady. Okay. So now you got a real estate lesson. So that's why stuff is expensive around there. Okay. So these tables are all very useful. Okay. So higher the specific heat, harder it is to change the temperature of that object. Okay. All right, now we'll talk about latent heat. Okay, so let's say you go to your freezer and get a bunch of ice, okay? And the ice from your freezer is about minus 5 degrees Celsius, okay? And you put it on the stove, what will happen? Huh? So it won't melt, it will warm up till it goes to 0 degrees Celsius. Okay. The initial heat you applied is raising the temperature of the ice. Once it gets to 0 degrees Celsius, now the temperature won't rise. Now the ice starts melting. And the temperature will remain constant. So here's the graph. So here's heat added. So this is that pan is on the stove. Okay. Okay, so let's say you got ice at minus 20 degrees Celsius. The temperature of the ice will rise till it gets to 0 degrees Celsius. And as you keep adding heat, now the temperature is constant. Yeah. The temperature is not changing. So where's all the heat going? Yeah, so it's to breaking the bonds. When in a solid, those water molecules are in fixed locations, so all the heat is going into breaking the bonds. That heat that is not raising the temperature, but which is contributing to the phase change of the material, that's called latent heat. Okay, and that is a very important thing. So the heat that goes into changing phase and not raising the temperature is called latent heat. So this is the amount of heat added. That's the amount of ice that melted, or the water that got converted to steam, and that's the latent heat. Okay. So you have two phase changes: solid to liquid and liquid to gas. Okay. So this is latent heat of fusion, which is when your ice is melting, and latent heat of vaporization when it's going from liquid to gas state. Okay. And so again, whenever you see a table for something, that means it's a very important thing. And so somebody's gone to trouble to make tables for this. So here's the material, here are various material. Latent heat of fusion is when you go from solid to liquid phase. And here's what this tells you is that's how much heat you need to melt 1 kg of ice. 1 kg is 2.2 pounds of ice. Latent heat of vaporization is that's how much heat you need per kg to vaporize water. Okay, these are extremely important numbers, and I'll give them to you in other unit. 80 calories per gram. What does that number mean?
What does it mean?
Uh-huh.
Like, how many calories it takes for 1 gram to go up to Celsius?
Yeah, so to melt 1 gram of ice, you need to add 80 calories of heat. Okay, that's what that number means. And this is 540 calories per gram. To vaporize 1 gram of water, you need 540 calories of heat. Okay. This is an enormous number. To warm 1 gram of water by 1 degree Celsius, all you need is 1 calorie of heat. Okay. Now we take advantage of this number especially. Okay. Again, biological systems use physics all the time. Okay. So what are these things? These are thermodynamic systems that operate optimally at 37 degrees Celsius. Okay. Now, they don't like the temperature to change much at all. The temperature changes by 1 degree Celsius and these systems start complaining. All right, so by the way, normally when you're just sitting there and complaining about this physics lecture, and you're producing 100 joules of heat every second. You guys are all like 100-watt bulb. All right, if your body is not getting rid of that heat, what would happen to your system? Your temperature would rise. So you're getting rid of 100 joules of heat per second. Let's send you for a run. And now suddenly you're producing 1,500 joules per second. You got to get rid of 1,500 joules per second. Your air conditioning has to operate 15 times harder, just like that. Ask this air conditioner to work 15 times harder. No way, Jose.
If it did,
What?
if it did, you wouldn't feel like you were heating up, or like you wouldn't get hotter from exercising, or?
No, what I'm saying is you're producing all that extra heat. You want to start getting rid of that extra heat faster. So how do we do that? We take advantage of this number. Okay? So what you do is you sweat. Are you done? Then what?
So we get back to the temperature that you.
So what you do is you sweat and then hope like hell your sweat evaporates.
Which is why.
Every time 1 gram of sweat evaporates, it takes away 540 calories of heat. Yeah. So that's our cooling system. So what happens if you set up a treadmill in a sauna and run?
Yeah.
Yeah, that's a fast way to kill yourself.
You'd be miserable first, but.
Yeah. All right, so what if you go for a run and the humidity is 100%? What if somebody overheats? We have plenty of people in the medical industry. Huh?
Heat stroke.
Heat stroke. So how do you cool people like this? What you do is you give them an alcohol rub. Why do you give them an alcohol rub?
Because it causes the water to evaporate.
What?
Causes the water to evaporate.
No, the water is not evaporating, but there's no alcohol in the atmosphere. It's 0% humidity as far as alcohol is concerned, and that will evaporate. The only thing is, when alcohol evaporates, it's taking up about 204 calories per gram. So now you know why we don't sweat alcohol. It's less efficient. Okay, water is 2.5 times more efficient. Okay, so anyway, so like I said, biological systems are very smart. Okay? They take advantage of all the object. Mhm. So when 1 gram of sweat evaporates, 540 calories of heat is taken away. Okay? Here's a very interesting number. Our cooling system is extremely efficient. It is claimed that people have survived temperatures of 124 degrees Celsius, 260 degree Fahrenheit. So the claim is the following. You put two things in an oven, that thing cooks and this guy walks out. We don't know if he has the appetite to eat that steak, but that's the claim. So your thermodynamic system is extremely amazing. Yeah. All right, here's, so again, these are latent heats that we're talking about. Latent heat of vaporization for water is 540 calories per gram, and latent heat of fusion for water is 80 calories per gram. Okay, these numbers are good to remember, useful to remember. Again, what is this number?
1 pound.
The amount it takes to change the heat by 1 degree.
This thing.
The plate.
No, this is to melt 1 gram of ice, you need 80 calories of heat, okay? So to freeze 1 gram of water, what would you need to do? Yeah, you have to take away 80 calories. Okay. And to condense 1 gram of water, what would you have to do? You take away 540 calories. Okay. So now you might understand something. This is 100 degrees Celsius, 1 kg of water. 100 degrees Celsius, 1 kg of steam. What would you have thrown at you? They're at the same temperature. Hmm? Yeah, why?
Less energy,
Oh, I'm sorry?
less energy overall.
Yeah, this steam will condense to 1 kg of water at 100 degrees Celsius, and every gram is adding 540 calories of heat. That thing will burn. And then the water will burn too. Okay. So steam burns are to be avoided. Okay, the next few slides, I'll show you how much energy is nature moves around. So here's one little piddly little lake, and this happens to freeze in the winter. Okay. About your height, 1.5 meter. So remember, when we were freezing lakes, you only freeze the top surface. So this is about 1.5 meters. Okay. This lake is about half the size of Florida. Okay, so the lake is about half the size of Florida. So to freeze this much water, you have to remove quite a bit of heat. You have to remove heat. Remember, to freeze 1 gram of water, you have to remove 80 calories of heat. So you want to cover Florida, half of Florida with this much ice, you got to remove quite a bit of heat. This is how much heat you have to remove. 10 million atom bombs worth of heat. So each winter, you remove that much heat. Again, how do you freeze a lake?
You reduce the external temperature.
Yeah, you reduce, remember? So you want to freeze a lake, you make this temperature cold, the air temperature cold. And you remove this. So each winter you're removing that much heat, 10 million atom bombs worth, and then 3 months later you change your mind and you melt the ice. And that's just one pretty little lake. All right, heat is transferred from a hot object to a colder object. And there are 3 mechanisms for heat transfer: conduction, convection, and radiation. So all 3 are illustrated here. So heat is being transferred via conduction to this person. Heat is being transferred via convection to that person. How is that heat being transferred?
Convection.
Yeah, but what is happening physically? So this flame is warming the air up. I'm sorry? No. Okay, so,
It's like a domino, just chain reaction, heat.
no.
To you.
Okay, so this air gets warm. When air gets warm, so PV equal to nRT, the pressure is the same. When the temperature rises, the volume increases. The volume increases, it gets less dense, and it rises up. So warm air rises up, and that's how you get warm. Okay? So convection is the warm fluid moving and taking heat away, okay, transporting heat. So, and this happens if you boil water as well. Okay, when you boil water, this water warms up, it gets less dense and it rises up, cold, getting replaced by cold water. Okay, So that's convective heat transfer. You actually have a fluid carrying heat. And here's heat transferred via radiation. Okay. So this is illustrating convection here. There's a candle burning on Earth. Okay. This air gets warmed up and it rises up, and you see the flame takes that shape. Here's a candle burning in the space shuttle. In the microgravity environment, there's no buoyant force, and so warm air is not rising up. Okay. Okay, here's a solid. This end is hotter than this end. How is heat transferred? This guy bumps into him, transfers some of his heat, and so on. Okay, so that's how heat is transferred. Again, there's an electron gas as well. We won't talk about that. So as engineers, we are interested in the following. We are keeping this room warm. Outside it's cold. So what's happening? There's heat flowing out. And there's dollars going out through that wall. Mentioned this before. Do you guys know how much money we spend on our electricity bill annually?
The school?
$5 to $6 million. Our budget is $100 million. Okay, almost 5% is an energy cost. And of course, we don't want that many dollars flowing out. Okay. Anyway, so the rate of heat flow depends on the area. The larger the area of this wall, the more heat will flow out. Okay. This is called the thermal conductivity. That's the area of the wall. And there's the temperature difference. Colder it is outside, the more heat will flow. Okay. So here, the higher the temperature difference, and this is the thickness of the wall. Okay. So that's the rate of change of temperature. So, and temperature is decreasing outside. So so that's the positive x direction, minus dt by d. This is negative, so there's the negative sign. That's the rate of change of temperature. That's the thermal conductivity. That's the area of the wall. Okay. Okay, so here's an interesting problem for engineers. Okay. Okay, so this room has a capacity of 100 people. If when between classes, when this room is empty, okay, you're not producing as much heat. When the classroom fills, 100 times 100, that's 10,000 watts. Okay, so your air conditioner suddenly has to pump out that much heat. Yep. In a server farm, a laptop, this thing is like a 100-watt device. That's a 100-watt device. So that thing is producing 100 joules of heat, the same as that guy. Okay, so you had to remove that heat. Yeah. In a server farm, 10,000 CPUs can have power consumption. So 10,000 CPUs in this room, you can have 10,000 CPUs easily in a server farm. Each is a 100-watt bulb. That's 1 megawatt. 1 megawatt is the same as 1,000 homes. So in this room, you produce 1,000 megawatts. That air conditioner had better not go down because it has my bank balance information. Well, that's nothing, but it has her bank balance information. She'll be pissed.
So is that why like AI has like a CO2 emission?
Oh, yeah, I mean, but once you produce all your electricity from solar and wind, and you're good. Okay? But that's the kind of engineering problems you have. Okay. Anyway, so the chip on top of the chip is sitting this metal conducting that heat, and then the fan blows away, removes the heat from the fins. All right, guys, we'll stop here.